Alright, so we're going to cover Chapter 11, Linear Regression. So in the last chapter, we explored the concept of correlation. We focused on Pearson's R, which measures the strength and the direction of the linear relationship between two interval or ratio level variables. So while correlation provides valuable insights into the association between variables, it does not allow us to make predictions or to understand the nature of the relationship in any level of depth. So this chapter on linear regression, which is going to introduce a powerful statistical method that extends the concept of correlation by enabling us to model and predict the relationship between variables. Linear regression helps to answer questions like, can we predict the value of one variable based on the value of another? Before we jump into regression, we're going to start with a quick review of linear equations. This information should look familiar from the algebra classes that we've taken in the past, but we realize that for a lot of students, the last algebra class could have been a really long time ago, so we're going to do a little refresher. So we're in section 11.1, review of linear equations, on page 1 of chapter 11. So as we recall, a linear equation represents a straight line when it's graphed on a coordinate plane. So in algebra classes, it was typically written as y equals mx plus b, right? So y like yes equals m like mother, x like x-ray, plus b like boy. Y equals mx plus b, where y is the dependent variable, x is the independent variable, m is the slope of the line, b is the y-intercept. So the slope tells us how much that y changes for every 1 unit increase in x. You may have heard this described as change in y over change in x, or rise over run. So the positive slope means that as x increases, y also increases. The negative slope means that as x increases, then y tends to decrease. The y-intercept is the point where the line crosses the y-axis on our coordinate graph. This is the value of y when x equals 0. For example, if you have the equation y equals 2x plus 5, then the y-intercept is 5. This means that when x value is 0, y equals 5. The y-intercept is crucial because it provides a reference point for the line, helping us to understand where the line begins before any change in x occurs. So to graph a linear equation, we can start by plotting the y-intercept on the y-axis. Then we can use the slope to determine the direction and steepness of the line. So for example, in the equation y equals 2x plus 5, you would start with your line on the y-axis and you would mark 5, and so that would be your coordinate 0, 5, right, in parenthesis, which is sometimes read as over 0 up 5. Then, because the slope is 2, you would move up 2 units on the y-axis for every 1 unit that you move to the right on the y-axis. So we can see a visual illustration in figure 11.1. Sometimes we are given the value of x and asked to compute y, or vice versa. So for example, with this equation, y equals 2x plus 5. If x equals 5, then what would y equal, right? So if we plug this in, so we would have 2x, so 2 times 5 is 10, plus 5 equals 15. And then we're moving on to page 2, and we're seeing our line graph. So this figure 11.1 is your graph of the line where y equals 2x plus 5. Okay. So thus, when x equals 5, we can compute that y equals 15. So when looking at figure 11.1, we can check that out, and coordinate 5 and 15, yep, goes right through that. So yes, the line does in fact pass through that 5, 15 in parenthesis coordinate. Moving into our next section, 11.2 on page 2, we're going to do an introduction to simple linear regression. So stripped to its bare essential parts, simple linear regression models are basically a slightly fancier version of our Pearson correlation. Though, as we're going to see, regression models are much more powerful tools. A simple linear regression model uses one interval ratio variable, right? So it could be interval or ratio, to predict a second interval or ratio variable. The predictor variable is known as the independent variable and is usually denoted as the letter big X. And your outcome or predicted variable is known as the dependent variable, and that's usually denoted with the letter big Y. So as we keep scrolling on page 2, we have a reminder of our data set that we were using with chapter 10, the parenthood data set. This visual that I'm looking at on page 2 is the Danny's grumpiness versus Danny's sleep. And so this is our scatter plot again of Danny's sleep and Danny's level of grumpiness. You could say it either way. And again, as we know, this slope of this line was negative. And right, so we can say that there's a direct negative relationship, as we recall, or a perfectly negative relationship. So like when Danny gets less sleep, right, her level of observed grumpiness will increase, right? So as we can see, that is exactly what happens. When she slept like 8 hours, you can see that her grumpiness level was about 50, but if she only slept like 4 or 5 hours, her grumpiness was really high. It could be about 90, between 80 and 90, if she slept under 6 hours. So again, since the basic ideas in regression are closely tied to correlation, we're going to go back and use our parenthood data file, okay, that data set. And so let's recall from this data set that we were trying to find out why right? Why is Danny so grumpy all the time? And our working hypothesis was that it's because Danny's not getting enough sleep. So then we drew the scatter plots to help us examine the relationship between the amount of sleep that Danny got and her level of grumpiness reported the following day. And again, we have our visual figure 11.2. And again, so as we saw previously, this corresponds to a correlation of R equals negative 0.903. What we found in this illustration is something that looks close to also the figure 11.3a. So let's go look at 11.3a. Oh yeah, okay. So Danny's sleep and Danny's grumpiness. Yep. So that's on page 3. So that is, we can mentally draw a straight line through the middle of the data. In statistics, this line that we're drawing is called a regression line or a line of best fit. Note that the regression line goes through the middle of the data. We don't find ourselves imagining anything like the illustration that is in 11.3b, right? We wouldn't draw the line of best fit that way, right? So that would be not the best fitting regression line. And in 11.3a, we can see that the best fitting regression line is drawn in visual A. So again, this is nothing surprising. The line that we drew, you know, it all makes sense. And let's see. So again, in the first section, 11.1, we saw our equation y equals mx plus b. This is the notation that is often used in our algebra classes. Note that the slope is the number attached to x and the y-intercept is the value that is standing alone, right? So in statistics, we use a slightly different formula that is usually written as the formula on page 3. Okay, so it's the approximate or estimated y subscript I equals, it looks like this is using beta 0 plus beta 1 and then big X subscript I. So let's translate this. So this looks different from our algebraic formula, but it's actually pretty similar when we break it down. So again, the predicted value of y with the subscript I, or estimation of that y, looks familiar, and that is again the dependent variable, and it's for the ith individual. Then we have our big X subscript I, which is the value of x, which is our independent variable for the ith individual. And then our y-intercept is the beta subscript 0, and the slope is beta subscript 1. So again, notice that in this formula we've written x subscript I, y subscript I, rather than just plain old x and plain old y. This is because we want to remember that we're dealing with actual data, right, in our data sets. In this equation, x subscript I is the value of the predictor value, variable. X subscript I is the value of the predictor variable for the ith observation. So for example, the number of hours of sleep that Danny got on day I of the little study, and then y subscript I is the corresponding value of the outcome variable, which is the grumpiness on that day that she took her data. And so although this author is saying that they haven't said so explicitly in this equation, the author says that we're assuming, what we're assuming is that this formula works for all observations in the data set. So example, for all of I. Then we're supposed to notice that the author wrote the estimation of y subscript I and not the y subscript I. This is because we want to make the distinction between the actual data y subscript I and the estimate y, estimated y subscript I. For example, the prediction that our regression line is making. Thirdly, the author changed the letters that were used to describe the coefficients from A and B to just like we'll say B or beta subscript 0 and beta subscript 1. That's just the way that statisticians prefer and like to refer to the coefficients in a regression model. A lot of people don't really know why they chose B, but that's what happened. And in any case, B subscript 0 always refers to the y-intercept term, and the B subscript 1 refers to the slope. So just like we saw in the formula used in the algebra classes, note that the y-intercept is always standing alone, and the slope is always attached to our x variable. All right, so we got that. So next, the author says that they can't help but notice that regardless of whether we're talking about the good regression line or the bad one, the data don't fall perfectly on the line, right? So to say that another way, the data y subscript I are not identical to the predictions of the regression model, right? The estimation y subscript I. So since statisticians love to attach letters and names and numbers to everything, right? Let's refer to the difference between the model prediction and that actual data point as a residual. We'll refer to it as, let's see, yeah, they're using like a E or an epsilon, a Greek symbol. So they're saying here, so let's back up, okay. So we have our equation originally of estimated y subscript I with the beta 0 plus beta 1 x1, and then our original was, hold on, we're gonna go back. Our original looked like y equals mx plus b. All right, let's go back. Okay. So we're at the bottom of page 3. And so since statisticians love to, again, attach letters and names and numbers to everything, let's refer to the difference between the model prediction and the actual data point as a residual. Okay, so that's a term. And we'll refer to this term as epsilon I equals y subscript I minus the estimated y subscript I, where again the e subscript I is our Greek letter epsilon, and it's traditional to use the e subscript I or just the little e subscript I in statistics, and it will denote residual. So then we can write down the complete simple linear regression model as we're at the top of page 4. So the simple linear regression model is now going to be y subscript I equals beta subscript 0 plus beta subscript 1 times x subscript 1 plus epsilon subscript I. So we're moving on page 4 into section 11.3, where we're going to be estimating a simple linear regression model. Okay, so now let's redraw some pictures that we've already drawn, but this time we're going to add some lines to show the size of the residual for all of the observations. So when the regression line is good, our residuals, like the lengths of the solid gray lines, they all look pretty small, right? So let's take a look. We're looking for figure 11.4a. Okay. And then we have 11.4b, so let's back up here. So when the regression line looks good, our residuals, or the lengths of the solid gray lines, they all look pretty small. But when the regression line is drawn in a bad way, the residuals are a lot larger. So that would be 11.4b. Okay. Okay, so maybe what we want in a regression model is small residuals. Yes, that would seem to make sense. In fact, the author is saying that they'll go so far as to say that the best fitting regression line is the one that has the smallest residuals. Or better yet, since statisticians seem to like to take squares of everything, why not say this? The estimated regression coefficients, so the estimated b subscript 0 and b subscript 1, are those that minimize the sum of the squared residuals, which could either be written as the sigma I yi minus estimated yi, and that would be squared, or as sigma I, and then we could substitute epsilon I squared, since yi minus estimated yi is actually epsilon subscript I. So that makes sense. All right. So again, we want to say what the author says here. It is worth making a note of the fact that our regression coefficients are estimates, okay? So we're trying to guess the parameters that describe a population, which is why I've added the little hats, right? The little estimation hats, so that we get beta, estimated beta 0 and estimated beta 1, rather than beta 0 and beta 1. Finally, the author is noting that since there's actually more than one way to estimate a regression model, The more technical name for this estimation process is called OLS, like Sam, or ordinary least squares regression. Okay, so let's keep going here. So at this point, we now have a concrete definition for what counts as our best choice of regression coefficients, right? For our estimated beta 0 and estimated beta 1. The natural question to ask next is if our optimal regression coefficients are those that minimize the sum squared residuals. So how do we find these wonderful numbers? The actual answer to this question is pretty complicated, and it doesn't help us, you know, as introductory level, right? It doesn't help us understand the logic of regression. So the author is saying this time they're going to let us off the hook, and instead of showing the long and tedious way first and then revealing the wonderful shortcut that our JASP statistical software uses, this author wants to just cut straight to the chase and just get into JASP and let the statistical software do all the heavy lifting and calculations, since that's why they made it. There is a subnote here, subnote 1. It says, at least they're assuming that it doesn't help most people, okay? Right? So when they said the actual answer to this question is complicated and it doesn't help you understand the logic of regression, there was like a footnote number 1, and it says at least this author is assuming that it wouldn't help most people to get into it. But on the off chance that someone reading this loves linear algebra, and to be fair, there are always a few of these people in the introductory statistics classes, it will help you to know that the solution to the estimation problem turns out to be estimated beta equals xx minus 1 x subscript y, where the estimated beta is a vector containing the estimated regression coefficients. The big X is the design matrix that contains the predictor variables, plus an additional column containing all ones. Strictly big X is a matrix of the regressors, but we haven't discussed this distinction yet. And then the little y is a vector containing the outcome variable. For everyone else who doesn't love algebra, this isn't exactly very helpful and can be a little bit overwhelming. So since quite a few things in linear regression can be written in linear algebra terms, you will see a bunch of footnotes like this one in this chapter, and if you can follow the math in them, great, but if you can't, JASP is going to do it for you. So we're at the top of page 5, where we're going to open up JASP and we're going to conduct a simple linear regression analysis. So again, it says we'll continue with the example using the parenthood data set. So let's take a look. So let's see. We did parenthood. Okay. So First, this author is going to take us through showing how to conduct the analysis in JASP. Then we're going to walk through each of the 3 tables that will appear in the JASP output. So we're going to do a simple linear regression. So again, we opened up our Parenthood data file, and it says here on page 5 that we're going to use the Danny Sleep and Danny Grump, okay? So we're going to use the Danny Sleep to predict Danny Grump. So in other words, again, the amount of hours that Danny slept is our independent variable, which JASP will call a covariate, and the Danny Grump, the grumpiness, is our dependent variable. So we're going to go into regression, and we're going to go into classical under linear regression. So regression, we're going to go into classical linear regression. We're going to move Danny Grump to the dependent variables box. So Danny Grump to the dependent variables box. And then we're going to move Danny Sleep to the covariates. Okay. And then we can compare what we got when we did this example with this screenshot that is on page 11.5. I'm sorry, this screenshot in figure 11.5. So let's see if it matches. So it says linear regression. So let's see. And we have the model summary for Danny Grump. Okay, so here. So we have R as big M subscript 0, 0.000 is the R. The R squared is 0.000. The adjusted R squared, 0.000. The RMSE, 10.050. M subscript 1, 0.903, 0.816, 0.814, 4.332. Then it's giving us something that we haven't talked about yet, this ANOVA. And there's a regression and a residual and a total. So this one, they rounded it to 8160. This one, they rounded it to 1839. The total is 9999. And then the degrees of freedom 1, 98, and 99. The mean square 8159.88, 18.76. We're getting these this F here that we haven't talked about yet as 434.9, and it looks like it's statistically significant. Underneath that, right, so we have coefficients here. So it says model, unstandardized, standard error, standardized, T, and P values. So let's go through this. So we have the intercept of M0 at 63.710 with a standard error 1.005 and a T statistic of 63.395, or you can round it to 63.40 with a p-value. M1 intercept 125.956, 3.016, 41.76 with a p-value. And then underneath that, it says Danny's sleep, negative 8.937, standard error 0.429, negative 0.903, negative 20.85, and p-values. Okay, so that's what we got. So it matches up. So again, we're still on page 5. And so we're going to say this next section at the bottom of page 5 is called a model summary table. So that must be what's at the top there. So again, in JASP, it gives us 3 tables by default. Okay, so we see that. And now we're going to walk through with the author of this textbook. So let's walk through each of these. So the first table is labeled Model Summary Dan Grump. Yep. This table has 2 rows, M subscript 0 and M subscript 1. So the null model is M subscript 0. This is a regression model with no independent variable. Okay, so it's essentially just y subscript I, which equals the beta subscript 0. So this is not what we want. We want the model that includes our independent variable. So what we actually want is the other row, the M subscript 1 row of the table. Okay, so this table, let's see, M subscript 1 is I believe this plus, yeah, 4 values. Okay, so this M subscript 1 has 4 columns. So it has the R squared, the adjusted R squared, and the RMSE. So this particular model only has one independent variable, which is known as simple linear regression, and the value of big R here is going to page 6. So here, as we said, the value of the big R is the absolute value of Pearson's R, and the R squared is the same as our R squared, or coefficient of determination, okay? And then that's what we saw in our last chapter, right, when we learned about correlation. The adjusted R squared, or the adjusted coefficient of determination value, is a modified version of the coefficient of determination, which takes into account the number of variables in the model. So this will be more useful when we get to the multiple linear regression later on, which will have more than one independent variable. And the RMSE stands for root mean square error, RMSE. So for a simple linear regression model, R squared is probably the only value on the model summary table that you're going to need. So here the R squared is 0.816. This is a large effect size. This means that when we move our decimal over 2 places, this means that 81.6% of variability in Danny's grumpiness can be explained by variation in how many hours of sleep that she had. So this next part is our ANOVA table, okay? So the second table is labeled ANOVA, which is our analysis of variance. So we'll see more of these later in the book. This table is testing the overall regression model, okay? So again, it stands for analysis of variance. So this table is testing the overall regression model. It is comparing our model, which contained one independent variable, comparing it to the null model, the M subscript 0, which didn't contain any independent variables. So essentially, these are the hypotheses being tested in the ANOVA table. So the null hypothesis is that the model does not predict big Y, and the alternative hypothesis, or H1, is that the model I'm not sure if there's a typo here. There might be a typo here. We may have to come back to that later. So again, I think the null hypothesis might be the same that we did last time, where the model does predict Y, and then the alternative would say that it does not predict Y. So let's keep reading, and then we can come back to, I think there's a typo on this page 5, or actually page 6. So a regression model is tested using an F-test statistic and the F-distribution. So the F-distribution is always positive. You'll see that the F-test statistic, again, let's see what it says here. It's positive for 34.9. So the F distribution has degrees of freedom just like the T distribution. The F distribution actually has 2 different degrees of freedom. So in regression, the JASP software will call these the degrees of freedom regression and the degrees of freedom residual. So here's the degrees of freedom regression and the degrees of freedom residual. Okay. And then there's a total, which looks to add them together. The author is saying that you may also hear these called the degrees of freedom numerator and the degrees of freedom denominator, respectively. So these are calculated with the following equations. So there's degrees of freedom subscript regression equals big K. There's degrees of freedom subscript residual equals N minus K minus 1. And then there's the degrees of freedom total, which is N minus 1. Okay, so in these equations, we're on page 6. K is the number of independent variables, and N, big N, again, is our sample size. We're going to use a little bit of algebra, and then we can determine the degrees of freedom total equals the degrees of freedom regression plus the degrees of freedom residual. Okay? All right, so then the numbers that we need to pull from the ANOVA table are the F-test statistic, its degrees of freedom, and the p-value. So in this case, the F-test statistic is 434.906 with 1 and 98 degrees of freedom. The p-value is very small at less than 0.001. So in APA style, we could summarize succinctly by saying F and then in parentheses 1 comma 98 close parentheses equals 434.91 comma p is less than 0.001. So because the p-value is less than the standard 0.05 alpha level, we will reject the null hypothesis, and this regression model is statistically significant. Okay. Then we have this table at the bottom called the coefficients table. So this is our third table, and it does have the top row, which is the M0. The null model, right, the M0, it only includes the y-intercept. Which just so happens to be the mean of the dependent variable. It does not include the independent variable. In this type of an introductory level, we're not going to be using this. What we want is to look at the data under coefficients for M subscript 1. This model includes the y-intercept, it includes our independent variable. So looking at our M1, the values in the column labeled unstandardized are the coefficients. So the y-intercept is 125.956. Okay, that's the unstandardized. And our slope is negative 8.937. All right. Putting this together, our regression equation is the estimated y subscript I equals 125.956 plus the negative 8.937, and then that gets multiplied by x subscript I. Also important in the coefficients table is the test statistic and the p-values. These test statistics and p-values are comparing the y-intercept and the slope to 0. Testing whether or not the y-intercept is different from 0 is usually not a relevant research question. The vast majority of the time, we're just going to focus on the slope. These are the hypothesis statements being tested for the slope. So the null hypothesis is that beta 1 equals 0, and the alternative hypothesis is that beta 1 does not equal 0. So in our output, the test statistic for our slope can be found in the row labeled with our independent variable, Dan's sleep. So the test statistic is the negative 20.854, and the p-value is 0.001. P-value is less than the standard 0.05 alpha level, so we will reject the null hypothesis. There is evidence that Danny's sleep can be used to predict Danny's grumpiness. Unfortunately, JASP does not compute the degrees of freedom for the t-tests in the coefficients table, but they are relatively easy to do by hand. For a simple linear regression model, the degrees of freedom for the y-intercept or the slope are equal to n minus 2. So now we're going to review interpreting a simple linear regression model. Okay, so let's review all of these key values that we pulled from our output. It's really important that you know which values that we need to focus on and how to interpret them. So let's start with the estimated beta subscript 1, the slope. So if we remember the definition of the slope, a regression coefficient of beta subscript 1, the estimated beta subscript 1 as the negative 8.937, means that if I increase x subscript I by 1, then I'm decreasing y subscript I by 8.937 grumpiness points. Okay, so that is, again, each additional hour of sleep that I gain will improve my mood, reducing my grumpiness by 8.937 grumpiness points. So what about the y-intercept? So since the estimated beta subscript 0 corresponds to the expected value of y subscript I and x subscript I equals 0, it's pretty straightforward. It implies that if Danny gets 0 hours of sleep, so x subscript I equals 0, then Danny's grumpiness will go off the scale. So to the extremely high value of like y subscript I equals 125.96, okay? But does it even make sense to interpret the y-intercept in this model? It is important to consider a value of x subscript I equals 0. Well, it is important to consider whether this value of x subscript I equals 0 is a reasonable or even possible value. In this scenario, this would mean no sleep, which is technically possible. But if we look at our scatter plot back in figure 11.2, the axis representing Danny's sleep does not actually go to 0. The minimum value was about 4.84 hours. So because our sample data does not extend right to x equals 0, we should not use this model to estimate y when to estimate y subscript I when x subscript I equals 0. This common mistake is called extrapolation. So now let's review the hypothesis tests that we could conduct from this output, okay? So first, we could conduct a hypothesis test for the overall model. The null hypothesis is that the model cannot be used to predict the dependent variable. The alternative hypothesis is that the model can be used to predict the dependent variable, okay? So that needs to be adjusted, I think, from the previous data that was mistyped. So hold on. We're on page 7. So this typo was on page 6. So the null hypothesis is that the model does not predict y, and the alternative hypothesis is that the model, there's a typo, but it say does predict y. So let me go back to page 7. The null hypothesis is that the model cannot be used to predict the y or the dependent variable. The alternative hypothesis is that the model can be used to predict the dependent variable. So to address these hypotheses, we used the f-test from the ANOVA table, which is that 434.9. So second, we could conduct a hypothesis test to determine if the slope is different from 0. This tells us if the independent variable is doing anything to predict the dependent variable. The null hypothesis is that the slope of beta 1 equals 0, and the alternative hypothesis is that the slope is not 0. So to address these hypotheses, we use the t-test, which is found in the coefficients table in the row for the independent variable. So at the bottom table. Also recall for simple linear regression, the results obtained from these two approaches will be identical. This is only true in simple linear regression. It will not be the case when we discuss multiple linear regression. So let's keep going. So how do we report a simple linear regression model in APA language or APA style? So if we want to report the results of this regression model in APA style, we have two different options. So because this is a simple linear regression model, we could report the f-test for the overall model or the t-test for the slope. So since simple linear regression models only have one independent variable, these results will be identical. So we could report the overall model this way. The regression model using Danny's sleep to predict grumpiness was statistically significant, and F, okay, so we're in the middle, F, and then 1,98, close parentheses, equals 434.91, comma, p-value less than 0.001, and then we get the r squared from the top model summary, and then we do comma r squared equals 0.82. Which is our coefficient of determination. Now there is a subscript, a footnote down here at the bottom. So here's a fun fact. An F distribution with one numerator degrees of freedom is equivalent to a T distribution squared, where the degrees of freedom for the T distribution are equal to the denominator degrees of freedom for the F distribution. So in this case, we can show that T squared equals F. So let's check that out. So T in the bottom, where it's M1, let me check. So if it's 41.76, times 41.76. No, I think it's this 20.85 times 20.85. Okay, it's the bottom row where it says Danny's sleep. because we're looking to see if this can predict grumpiness. So in the T column, all the way at the bottom, the negative 20.85 times negative 20.85 gives us the 434 F value. So that makes sense. Okay, let's go back to page 7. All right, so we got that. Then we move to page 8. So note that it's common to report the coefficient of determination with the model. This is used as a measure of effect size. We could also choose to report the statistical significance of this model in terms of the slope for the independent variable. So in the simple linear regression model, Danny's sleep was a significant predictor of her grumpiness. And then T, 98 equals negative 20.9. Okay, that makes sense because it's n-1. So T parenthesis 98 equals negative 20.9, comma P less than 0.001, comma R squared equals 0.82, and that's from the top table. So again, with a simple linear regression model, because there is only one independent variable, the results will be the same using either of these methods. So later on in the chapter, we are going to get into the multiple linear regression, which has 2 or more independent variables. And at that point, you will need to carefully consider whether you want to report overall model or specific slopes. Next, we're going to get into the assumptions of linear regression. Okay. So we are on page 8, section 11.4, assumptions of simple linear regression. So, the simple linear regression model that we've been discussing relies on several assumptions. Many years ago, when this author was in graduate school, the author is saying that they learned these using the acronym, these assumptions using the acronym LINE, L-I-N-E. So let's take a look at each of these assumptions now. So again, we have linearity. So this is our pretty fundamental assumption of the linear regression model, is that the relationship between x and y actually has to be linear. If the relationship is not linear, then there are more advanced methods you could consider, but we're not going to get into that in this intro course. You can check this assumption by visually inspecting your scatter plot. So the line of best fit for your data points should be a straight line. Independence of errors is the next part of our line acronym, so the I portion. So recall that error is a synonym for residual. This is really just a catch-all assumption to the effect that there's nothing, funny going on in the residuals. If there is something kind of strange, like for example, if the residuals all depend heavily on some other unmeasured variable. So if there is something, kind of strange going on, this could, mess things up. You can check this assumption, the independence of errors, right, or residual. And we can check this assumption using the plot of residuals versus predicted values, which we're going to get into in JASP in a little bit. And then on this graph, there should be no clear relationship between the residuals and the predicted values of y. The N of line acronym is normality of residuals. So like many of the models in statistics, linear regression relies on an assumption of normality. Specifically, it assumes that the residuals are normally distributed. It's actually okay if the predictions of x and outcome y are not normal, as long as the residuals are normal. So we can check this assumption by making our histogram or even the QQ plot of the residuals, and we'll do that in JASP. Then there's LINE, so the equal error variances, which is also known as homoscedasticity. Homoscedasticity is a really tricky word. It means equal spread, okay? This means that the variance of the residuals should be constant across all levels of the independent variable. This means that the spread of the residuals should be roughly the same for all of your predicted values. You can check this assumption using a plot of residuals versus the predicted values and then looking for the consistent spread. So in addition to these four assumptions of simple linear regression, there is a fifth that is sometimes included, and that is that there are no outliers, right? No really significant or bad outliers. So it's not actually a technical assumption of the model because it's sort of implied by all of the others, but there is an implicit assumption that your regression model isn't being too strongly influenced by one or two anomalous data points, because this then raises questions about the adequacy of the model and the trustworthiness of the data in some cases. So this assumption can also be checked by looking at your scatter plot. All right, so we're moving into 11.4. 11.4.1. We're going to go from bottom of page 8 to page 9. So we're going to be checking assumptions in JASP. So we're going to go back to our parenthood data set to see how to create and interpret the plots that we need to check for the assumptions. So we're now moving to page 9. So for linearity, right, L-I-N-E, linearity, acronym LINE is L. So the first thing is we have already learned several ways to make a scatter plot in JASP. But here's a quick review of one approach for the purpose of checking the assumptions of normality and outliers. This author prefers to make the scatter plot without the line of best fit, and by default, JASP will assume a linear relationship regardless of the shape of the actual relationship, which the author finds to be misleading. So let's follow our description, and we're going to go into descriptives. Open up descriptive statistics. Okay. And then we're going to move Danny Sleep and Danny Grump. Into the variables box. We're going to go under customizable plots, and we're going to check scatter plots. Okay. And under scatter plots, we're going to uncheck the box next to add regression line. Uncheck it. There is the option that you can remove the density plot by selecting none under graph above scatter plot and graph right of scatter plot. So you could click none. Okay. So let's double check it against the figure 11.6 on page 9. So it looks exactly the same. Okay. So we have our scatter plot of Danny's sleep versus Danny's grumpiness. Okay. The relationship between Danny's sleep and Danny's grumpiness, it does appear to be linear. There is a consistent downward trend. And if we were to draw a line of best fit through these data, then we would end up drawing the straight line. So thus the assumption of linearity has been met. And from this scatter plot, we can see that there are no univariate or bivariate outliers. That means that there are no data points that are extremely different from the general trend. Moving to page 10. Now we're going to look at independence of errors, so the I part of our line acronym with our assumptions. So next we're gonna make a plot of our residuals versus predicted values in JASP. So on this graph, we want to see no relationship between the residuals and the predicted values. So to do this, we're going to create a plot of residuals versus the predicted values. So we're going to go to regression, classical, linear regression, and we're going to move Danny's sleep into the dependent box. Danny's sleep into the covariates box. And we're going to move Danny's grumpiness into the dependent . Okay. So under plots, we're going to check the box next to residuals versus predicted. So go plots, residuals versus predicted. Okay, let's see what that looks like. So we're on page 10, figure 11.7, and it looks the same. So this is what we want to see. We want to see no clear relationship between the residuals and the predicted values. So it basically looks like a blob. And in this particular part of our assumptions, okay, so in the independence of errors, we want to see a blob, all right, and this is good, okay, we meet that assumption. The next assumption is normality of results, so L-I-N-E. So to check the assumption of normality, we can look at a histogram of the residuals or a QQ plot of the residuals. The author prefers the histogram, but some statisticians like QQ plots, so we're going to show both. So we're going to move down to the bottom of page 10. We're going to create a histogram and a QQ plot. So again, we do regression, classical, linear. We move Danny's sleep to the covariates, Danny's grumpiness to the dependent box, and then go to plots. And under plots, we're going to check the box next to residuals histogram. Okay. And then we're also going to check the box QQ plot of standardized residuals. And then let's check our output against figure 11.8a and 11.8b. Looks the same. So we have a histogram of standardized residuals and we have a QQ plot of standardized residuals. Okay. And we're looking for normality. Looks okay. So these are standardized in that they are converted to z-scores. If you'd prefer to see the raw residuals in JASP under residuals histogram, you can so to see the raw residuals in JASP, you can go under residuals histogram and you can uncheck the box next to standardized residuals. The shape of the distribution, it should be the same, and it is. It will just keep the values on the on the x-axis in the units of the dependent variable. So the histogram of standardized residuals looks similar to a normal distribution, so this assumption is met. Similarly, you could choose to use the QQ plot instead, and on this graph we want to see most of the data points falling very close to the diagonal line, the red line. So then the E part of our assumptions, LINE, is equal error variances. So our fourth and our final assumption is equal error variances. To check this assumption, we're going to use the plot of residuals versus predicted values that we made when we checked the assumption of independence of errors. And this time when we look at that plot, we're looking to see if the variance of the residuals is relatively consistent across predicted values. So we're going to look to figure 11.9. Okay. And that shows up on page 12. So the author has attempted to draw some vertical lines on the plot of residuals versus predicted values to demonstrate what they were looking for. And what we want to see is relatively consistent variability among the residuals as you move from left to right on the graph. So again, the figure 11.9 on page 12 is your plot of residuals versus predicted values. And that's what it looks like. All right, so now we're at the bottom of page 11. We're in section 11.4.2. So what happens if your examples, what happens if your assumptions are not met, right? So hold on, let's see. So we did LINE. But what happens if we have violations, right, of LINE? So let's see. So in our example that we've been working with, we did have all assumptions being met with the parenthood data set and Danny's sleep and Danny's grumpiness. All of the graphs that we saw were exactly what we want to see, because that's what that data set was designed to be used for. But we're going to now show some examples of what these graphs would look like if the assumptions were not met. So let's first look at a violation of linearity. Okay, so we're just doing some examples in the text PDF on page 12. So there's an example of a scatter plot in figure 11.10. Figure A and figure B, there's scatter plots of non-linear relationships between X and Y. So for those scatter plots, the assumption of linearity is not met, and the relationship between X and Y is actually exponential. And it would not be appropriate to use simple linear regression to estimate those relationships. Also in the figure 11.10b, that is a nonlinear relationship. In that scatter plot, there appears to be a positive relationship between X and Y until X is about 5, and then at that point the relationship goes negative. So in this case, that would also not be appropriate to use with simple linear regression. Now we're on page 13. So what would it look like if there was a violation of independence of errors? So let's recall that we checked the assumption by looking at a plot of residuals versus predicted values, okay? So we don't want to see any sort of relationship on this plot. So let's look at these examples on page 13. We have 11.11a, which was constructed with using this using a data set where okay, we have two data sets, 11.11a and b, and it was constructed using the same data set that we just saw in 11.10a and b. So both of these plots of residuals versus predicted values, they actually show a clear relationship. So the assumption of independence of errors is not met in either case. Again, these 11.11 plots of residuals versus predicted show the assumption of independence of errors. The independence is not met. How about violation of equal error variances? So while we're looking at the plots of residuals versus predicted, this seems to be like a good time to also discuss the violations of equal error variances, says the author. This assumption is actually met. They're saying this assumption is met in figure 11.11a and b because the variability of the residuals is low across all predicted values. So for an example of when this assumption would not be met, we're going to look at the data on figure 11.12. This plot they're saying that this plot is what they are calling a funnel shape. And in this case, there is a lot of variability for the lower predicted values and less variability for the larger predicted values. This tells the author that this model tends to be less accurate when predicting smaller values and more accurate when predicting large ones. So this is a problem because simple linear regression assumes that these residuals are equally dispersed for all predicted values. Therefore, in the case of the data that's shown in figure 11.12, the assumptions of equal error variances is not met and simple linear regression should not be used. So there's 11.12. It's a plot of residuals versus predicted values. And it's an example where the assumption of equal error variances is not met. Moving to page 14. What about the violation of normality of residuals? So this is the last one. Recall, we want to see normally distributed residuals, and we've evaluated normality many times before. We use the histograms and the QQ plots, so this is probably the easiest violated assumption for us to identify. So the histogram that we can see in 11.13a and the QQ plot in 11.13b, those were made using the same data set. And And these both show that the residuals for this model are not normally distributed. From the histogram, there are a few that are notably larger than most, and looking at either graph, we can see that the assumption would not be met. So again, figure 11.13, those are two different plots used to check for normality of residuals. So checking assumptions, it's a lot of work, but it is a crucial step. Before interpreting the results of a regression model, we always want to check these 4 assumptions first, L-I-N-E. So understanding these assumptions, it is essential for accurately interpreting regression results. And it's essential for ensuring validity of our statistical inferences. So before the author is wrapping up this chapter, the next section we're going to get into is introduction of a multiple linear regression. And this technique is going to be similar to the simple linear regression, but it does involve 2 or more independent variables. So the author is not going to delve into all of the details of the multiple linear regression in this course because it's very complex behind the scenes, but we will briefly look at it. And they're going to highlight a few key aspects that we're going to encounter when reading published research.